This tutorial will cover a detailed introduction to the rotational world. Similar to the linear world, the rotational world is a part of everyday life, and we need to develop different ways of expressing and quantifying motion in the rotational world. So we'll start off by introducing angular or rotational terminology, which will allow us to talk about rotational kinematics, very much like what we've done before. So once we've familiarized ourselves with rotational kinematics, we can move on to rotational kinetic energy and moment of inertia, which will be used in an updated law for the conservation of energy that we can apply to questions related to rolling motion. When objects were moving in a straight line or at an angle, it was useful to establish a coordinate system. So you would usually have an origin point and an x or a y direction where the object could relate to, so that we can measure the object's position, velocity, and acceleration. So in the linear world, our coordinate system would look something like this, where we have an x and y direction, however we choose. But in the rotational world, we need something else. So just as you suspected, in the rotational world, things rotate, which means we need to look at things going counterclockwise or clockwise. So we need to come up with terms to be able to describe this behavior. So linear terms are really useful in describing things that move in a straight direction, but are linear terms really useful in describing objects that are rotating? Probably not, and we probably want something more convenient. Therefore, we need to define angular quantities that are analogous to an object's linear position, velocity, and acceleration. As a general summary, we used to use x for position, we used v for velocity, and we used a for acceleration. In the rotational world, we wanted to define 3 new terms for these quantities. We want to use theta for angular position. We want to use omega for angular velocity. And we want to use alpha for angular acceleration. So let's start by drawing a circle and defining these various angular quantities. So let's start with a discussion of angular position theta. Angular position is the angle that the object is at from a reference line, where theta equals 0 degrees or 0 radians. So with our circle, let's first draw this. We have, actually let's draw it on the left side. We have our circle. We have the axis of rotation. And we have a reference line. So the reference line can be this right here, where it is 0 degrees or 0 radians. So then angular position in green, if we have an object over here to start and it somehow moves over to this position, then it has changed angles from the reference point or the reference line. So this is the new position. We can call this theta f, and therefore the original position as theta I. We then have a certain angle, theta, that is traveled, and this is going to be equal to the displacement, or the angular displacement. So it's theta f minus theta I. So pretty much just like our x values when we had a displacement in the linear world, we had xf minus xi is equal to delta x. We now have angular displacement being delta f, not theta f minus theta I. So another thing we want to look at is what counterclockwise and clockwise directions are. So with anything moving around in a circle, we do have some sort of rotation or angular velocity, and if it's getting faster and faster, that means there's also some sort of angular acceleration we have to consider. So we'll just draw these curved vectors to represent these two quantities. A few things to note. By convention, counterclockwise, where theta is less than 0, is positive, and clockwise, where theta is greater than 0, is negative. The reason for that is because of our Cartesian coordinate system. We usually have this, and we usually start with this being 0 degrees, and we have 360 degrees going in the counterclockwise direction. So next, the units for angular position are in radians. And what exactly is a radian? A radian is the angle for which the arc length on a circle of radius r is equal to the radius of the circle. So let's write this definition down and try to make sense of it. So a radian is the angle for which the arc length on a circle of radius r is equal to the radius of the circle. So apart from that, we should probably define the arc length as well in order to define the radian. The arc length is given by an equation S equals to r theta. And where does this come from? If we do a full 360-degree revolution, which is one full revolution, on a circle, the radius of the circle is r, so we can draw this out. That's the radius of the circle, r. And the arc length is the circumference of the circle. So the arc length is basically the length around the circle, or the path that the object takes around the circle at a specific degree. So if we do a full 360-degree rotation, that means that the object has moved a total distance or a total arc length of 2 pi r. So the circumference is equal to 2 pi r. So that means one revolution is equal to 360 degrees, which is equal to 2 pi radians. But commonly, we don't really just want to look at one angular position. We do want to look at the angular displacement. So, apart from knowing angular position, we want to know angular displacement delta theta. And that is simply a change in position. So we have delta theta being equal to theta f minus theta I, and that is one of our main definitions that we need to know. So moving on, we've already covered displacement. We want to cover angular velocity omega. So angular velocity is defined as angular displacement over time, just like its linear counterpart. So now we have an expression for the average angular velocity. So we have omega average is equal to the displacement over a change in time. If the angular velocity is constant, then that means omega is simply equal to the average omega, which is equal to delta theta over delta t, which means that for one revolution, delta theta is equal to 2 pi radians, and delta t is simply equal to t, the period of one revolution. This means that using our equation for angular velocity, it is possible to create an equation for the period of rotation. So that means we have omega equals to delta theta over delta t, but for one revolution we know that 360 degrees is 2 pi radians, and the time it takes is just the period. We now have an equation for period, which is t equals 2 pi over omega. So there's another important equation. Last, we have angular acceleration alpha. So the angular acceleration is defined as the change in angular velocity over time, pretty much like its linear counterpart. We can then create an expression for the average angular acceleration in units of radians per second squared, or seconds to the power of -2. So one thing I forgot to mention, for angular velocity, the units are going to be radians per second or inverse seconds. Now for angular acceleration, the average angular acceleration is just the change in angular velocity over a change in time. So these are also important equations to know. The units would be radians per second squared. In the linear world of kinematics, we know that the acceleration due to gravity is constant. From that, we can get a set of kinematics equations that we can use. But what about the rotational world of kinematics? Well, if we say that the angular acceleration is constant, couldn't we use the same set of kinematics equations with our angular quantities? So let's write these out, but first let's jot down what linear quantities relate to which rotational quantities. So we simply want to go through different types of quantities. In the linear and rotational worlds. So first we do want to go through, say, displacement, velocity, and acceleration. We've already come up with displacement in the linear world as delta x. We know that it is delta theta in the rotational world. We know that velocity is v in the linear world, and we know that angular velocity is omega. Acceleration is a in the linear world, and acceleration is alpha in the rotational world. Now let's look at some kinematics equations. We had 5 different kinematics equations, so we'll do kinematics equations here. Our first one was Vf equals to Vi plus At. Our second one was delta x equals to Vit plus 1/2 At squared. Our third one was another version of number 2, which is Vft minus 1/2 At squared. We also had delta x being equal to 1/2 of Vi plus Vf times t. And our last one, we have Vf squared equals to Vi squared plus 2a delta x. So now we want to see if there are rotational versions of these, and there are. So these ones are going to be pretty much the same. We're just swapping the letters for our new definitions in the rotational world. We have omega f. Let's say this is number 1. Omega f is equal to omega I plus alpha t. We have delta theta being equal to omega I t plus 1/2 alpha t squared. Delta theta is equal to omega ft minus 1/2 alpha t squared. We have delta theta being equal to 1/2 of omega I plus omega f times t. And the last one, omega f squared is equal to omega I squared plus 2 alpha delta theta. So we now have a completely new set of kinematics equations that we can use for rotational kinematics problems. So when we solve kinematics problems involving rotation, we simply apply these newly defined angular kinematics equations in the same way we did the linear ones. So the best way to do this is to go through a couple of problems so that you get used to solving rotational kinematics. In this problem, you are playing fetch with your dog. You throw a ball with an initial angular speed of 36 radians per second, and your dog catches the ball 0.595 seconds later. When your dog catches the ball, its angular speed has decreased to 34.2 radians per second due to air resistance. A, what is the ball's angular acceleration, assuming it to be constant? And B, how many revolutions does the ball make before being caught? So let's first make a plan. This is our first venture into rotational kinematics, but the approach is almost identical to linear kinematics. We just need 3 parameters in order to solve for a fourth using one of the kinematics equations. So we have an initial angular speed, a final angular speed, and time that are given to us. This means that we can easily solve for alpha, or angular acceleration, using a kinematics equation for part A, and then determine angular displacement delta theta to answer part B. So what are the steps? Let's first draw a diagram and state our known values, just like we did with all of our previous kinematics questions. So we draw a diagram and state our known values. Although a diagram isn't necessary for this question, we should probably get used to labeling some items in the rotational world. So let's draw our person as a rectangle with arms and legs, and this is you, and you're tossing a ball. So this ball has some sort of angular angular velocity I, and it's going to travel all the way across and have a final angular velocity when your dog catches it. So let's write down what values we're given. We have omega I being equal to 36.0 radians per second, omega F being equal to 34.2 radians per second, T being equal to 0.595 seconds, delta theta equals to an unknown amount, and this is for part B, and we need to solve alpha for part A. So step number 2, we want to use our kinematics equations to solve. If we look back at our diagram, in order to use kinematics equations, we do need to have a coordinate system. So why don't we say this is positive, the clockwise direction, since we've drawn all of our rotations that way anyways. So we have let's just say part A is asking us to solve for the angular acceleration of this scenario. We're given omega I, omega F and T, and we're trying to solve alpha, so we use omega F is equal to omega I plus alpha T. Alpha is equal to omega F minus omega I divided by T. We just plug in our values, 34.2 minus 36.0 divided by 0.595, and alpha is equal to negative 3.025 radians per second squared. So that is our answer for part A. Next, we want to solve for part B. And part B is asking us to solve for the number of revolutions that the ball makes before it's caught. So we're going to have to find the angular displacement delta theta and then convert it into revolutions. So first step is to find delta theta in radians and then convert to revolutions. So we use the kinematics equations once again. We are given omega I, omega f, and t already, so we can use this equation. And just plug in the values. We have 36.0 plus 34.2 times 0.595. Delta theta is equal to 20.8845 radians. So we know that one revolution is equal to 360 degrees, which is 2 pi radians. So in one revolution, there are 2 pi radians. That gives us our conversion, and we have 3.324 revolutions that take place before the ball is caught. And that answers part B as well. In this problem, a pulley rotating in the counterclockwise direction is attached to a mass suspended from a string. The mass causes the pulley's angular velocity to decrease with a constant angular acceleration, negative 2.10 radians per second squared. A, if the pulley's initial angular velocity is 5.4 radians per second, how long does it take for the pulley to come to rest? And B, through what angle does the pulley turn during this time? So, once again, this is a kinematics problem. We do have angular acceleration, initial velocity, and final velocity because the pulley comes to rest. This means we can use a kinematics equation to solve for time in part A and then displacement in part B. Let's start with drawing a diagram. So we do need to draw a diagram to get used to rotational motion. Let's figure out what is happening at the initial and final stages. So initially, you have your pulley, like this. There's the axis of rotation right in the center, and it's turning with an initial angular velocity. The question does say that it's rotating in the counterclockwise direction, so make sure you get the direction correct. We can also say that the counterclockwise direction is positive. Next, there's a mass suspended from a string. So the assumption is there's a string wrapped around this, and it's pulling a mass up. So we have m over here, and then it's moving up with an initial velocity. So that's the initial stage. Then we look at what's happening in the final stage. We have our pulley again. It's going to stop, so we know that omega f, or the final angular velocity, is going to be 0. So we have here omega I is equal to 5.4 radians per second. Here we have omega f is equal to 0 radians per second. What else is there? We do know that we have our string. And the mass has also stopped moving, so its linear velocity is going to be 0. So let's write this down here. Vf is also 0 meters per second. So we have initial angular velocity, final angular velocity. We're also given angular acceleration. So that is equal to negative 2.10 radians per second squared. That makes sense. It means that we have angular acceleration going in the opposite direction of the positive direction. We're trying to find time, and we're also trying to find delta theta. So essentially that's how far this has turned. So step number 2, we can see we have a kinematics problem, so all we really have to do here is just apply our kinematics equations and solve. So let's start with part A. We're asked to solve for the time it takes for the pulley to come to rest. We have 3 parameters, so as soon as we have 3 parameters, we can pick the right kinematics equation to solve for t. So I do have omega f, omega I, and alpha in the rotational world, which means I can solve for omega f equals omega I plus alpha t. We want to solve for time t, so that's omega f minus omega I divided by alpha. That is equal to 0 minus 5.4 divided by negative 2.10. Time is equal to 2.571 seconds. So that's our answer to part A. Part B is asking us to solve for the angle the pulley turns during this time. So we want delta theta. So we already have omega I, omega f, and alpha. This one kinematics equation has a 4th parameter for delta theta, so we're going to use omega f squared is equal to omega I squared plus 2 alpha delta theta. We'll just rearrange for delta theta and get omega f squared minus omega I squared divided by 2 alpha. We do know that the final angular velocity is 0, so that goes to 0. So that means we have negative 5.4 squared divided by 2, negative 2.10. And delta theta is equal to 6.943 radians. Therefore, the pulley turns 6.943 radians to come to rest. With all this talk about linear and rotational quantities, we've kept the analysis separate. But what if there's a question that involves both? We'll have to figure out a way to connect the two worlds together. So let's try and see if there's a way to do this, and it all starts by looking at a rotating object that follows a circular path. So when you take a snapshot of that circular rotating motion, that object is moving in a direction tangential to the circle. So just as an example, we want to take a look at an object traveling around an axis of rotation. So we have our object, and it's moving around in a circle. And this is our axis of rotation. So when you take a snapshot of that circular rotating motion, the object is going to move in a direction that's tangent to the circle. So this is its tangential velocity. it has a linear speed and therefore a linear acceleration. So let's first take a look at speed. We know that the angular velocity of this object spinning around in a circle is omega. From our equation for the period t, we know that angular velocity is omega, and we know that the period is t equals to 2 pi over omega. So that means omega is equal to 2 pi over t. So how can we relate this to tangential speed, or Vt? Well, similar to our experience with circular motion and centripetal acceleration, the tangential speed is going to be calculated by how much distance the object travels in a given amount of time. So, the tangential or linear velocity is given by Vt is equal to the distance traveled over time, which is essentially 2 pi r for the circumference of the circular path divided by the time it takes to complete one revolution, which is just the period. So then we can write Vt, so tangential speed, as r 2 pi over t, and we just saw that omega is equal to 2 pi over t, so therefore tangential speed is equal to r times omega. So this is a handy conversion equation if you ever want to have a direct relationship between the linear and rotational speeds. Now let's take a look at acceleration. So we know that angular acceleration, let's say angular acceleration in the rotational world is given by alpha equals to delta omega over delta t. If we look at tangential acceleration, that's just at is equal to the change in tangential velocity divided by the change in time. So we already figured out Vt is equal to r omega, so let's say delta r omega divided by delta t. The radius is never going to change, so we can factor that out, and we get delta omega over delta t. But we know that alpha is equal to delta omega over delta t, so therefore we can say tangential acceleration is equal to r times alpha. So this is another equation that's good to remember to give us a direct relationship between linear and rotational acceleration. But we also know that in the linear world there's going to be centripetal acceleration. So there's another one, centripetal we have centripetal acceleration defined by ACP is equal to v squared over r. So we know that v is equal to r omega divided by r. The r and at the top and the bottom, one cancels out, so we're left with r omega squared. So therefore, we have a third relationship. We have ACP is equal to R omega squared. So keep in mind, this is tangential acceleration, and this is centripetal. Acceleration. And we might as well label this top one as tangential velocity. So now that we can relate the linear and rotational worlds, it's time to revisit and update some topics from the past, specifically with respect to rolling motion and rotational kinetic energy. Previously, we've only looked at objects moving from one point to another without any spinning or rotating. So what if we combine both? What if there's a ball rolling down a hill that's also rotating? We'll need additional tools to help analyze such scenarios. When we look at rolling motion, it's a combination of translational and rotational motion. So rolling motion it's a combination of translational and rotational motion. So think of an object of radius r, like this, that rolls or rotates with an angular speed of omega, and translates or moves with a linear speed of v. That means we need to consider the kinetic energy in both the linear and rotational worlds and add them up to get the total kinetic energy in an object that rolls and moves at the same time. So we already know that translational kinetic energy is given by 1/2 mv squared, so that's familiar to us from the linear world. We're going to call this KET, so we know that it's translational kinetic energy. It's 1/2 mv squared. Now we take a look at rotational kinetic energy. We're going to call this KER, and we need to figure out a way to express or come up with another equation to help define this. Since we already know that linear velocity or linear speed is equal to v equals to r times omega, it means I can rewrite KET as 1/2 m and replace v with r omega so that we can make that connection to the rotational world. This means I can write this as 1/2 mr squared omega squared. So this is looking very similar to our equation for translational kinetic energy. Both are in units of joules. But it also may be more convenient to express mr squared as something else called the moment of inertia I. So we want to express this as something called I, or the moment of inertia. That's going to simplify our equation to KER equals to 1/2 I omega squared. So we have this 1/2 mv squared for translational kinetic energy, and we have 1/2 I omega squared for our rotational kinetic energy. But now we want to talk about the moment of inertia. The moment of inertia is considered the rotational equivalent of mass. In other words, just like how mass determines how much force is required for a certain amount of acceleration, the moment of inertia is going to determine how much rotational force, or torque, is required for a certain amount of angular acceleration in the rotational world. The moment of inertia is going to express an object's tendency to resist angular acceleration. So just like how in the linear world, a larger mass is going to resist linear acceleration, a larger moment of inertia is going to make the object resist angular acceleration. So we're going to define the moment of inertia as I equals to mr squared. But is this equation always true? The answer is no. Because the moment of inertia depends on the particular shape or mass distribution of an object. So I depends on the mass distribution and shape of the object. When we calculate the rotational kinetic energy, we're trying to calculate the total rotational kinetic energy of the rotating object. So a full 360 degree or 2 pi radian spin. That equation we've presented up there is just the moment of inertia at a particular point in the shape. So just as an example, let's say we have our object here and it is spinning. If we want to calculate the total moment of inertia, we need calculus. But long story short, we can take a look at a hoop of total mass m and radius r as an example. Or we can also mimic this as an individual point object, like we've drawn here, that moves around in a circle to trace out this circular hoop. So I have an axis of rotation, and I have a hoop of total mass m, so the total mass is m, and we also have a radius being r. So let's use this as capital R. In order to figure out the total moment of inertia, we would need to break up the entire object into infinitely small elements and consider their individual contributions to the total moment of inertia. So over here, I have mi, and this mi represents the mass of each individual element, and essentially in calculus we would break this up into many tiny little masses around the entire circle. So the more times you cut this up, the more accurate your calculations will get. With calculus, you can break this up into infinitely small pieces, but let's assume every individual piece has a mass of mi, and every individual piece also has a specific distance from the axis of rotation, and we call this ri. In the case of a uniformly distributed circle or a hoop, Your Ri is simply just capital R, or the radius, for every single tiny element. So I'll just write down here, Ri is the same around the hoop for each Mi. And we also have individual elements of mass Mi that sum up to a total mass of capital M. So just to summarize, we then have a new equation for the moment of inertia. I is equal to the summation of all of our individual masses times the distance it's away from the axis of rotation squared. So for the hoop example here, we know that the total mass of the hoop is m, so all the little mi should add up to capital M. So in the case of I hoop, our total mass is going to be m. And we also know that the distance away from the axis of rotation, which is the center of the hoop, is capital R, so Ri is the same for each small element. So for a hoop, the moment of inertia is mr squared. So this is the same as this, because it's the simplest case. But what about a solid disk? If we have the same total mass m and form a uniform disk of the same radius r, the moment of inertia, as expected, would be different. Why? Let's draw this here. What about a solid disk? So if we had a solid disk here, you could have an outer hoop, but you also have to remember, if we have a solid disk, there would also be additional hoops inside the hoops so that it can form something that's solid. So as you can see, there's tons of different hoops that I've drawn just to represent a solid disk. And the key thing here is that all of these will have to be broken up into their individual elements. And when they're broken up into their individual elements, each one will then have different values of Ri. So it's no longer Ri is equal to R for all cases of Mi. You have these mi's at the outermost ring having a radius of capital R, but then you have these mi's in blue that have a different radius, Ri. So we have to be careful when we're looking at moment of inertia, because different shapes will have different values. So back to our question about the solid disk. If we have the same total mass m and form a uniform disk of the same radius r, the moment of inertia will be different because we have I of disk does not equal to I of hoop, because Ri is not equal to capital R for each individual element Mi. The elements at the outermost ring of the solid disk will have Ri equals to capital R, but the elements within the solid disk will have a value of Ri that's less than the radius down to the central element here, where R is equal to 0. That means that the contribution from the small elements to the overall moment of inertia will get smaller and smaller as your element gets closer to the center of the disk. It then makes sense that the overall moment of inertia for a solid disk is going to be less than the overall moment of inertia for a hoop. After a detailed calculation with calculus summing over all the mass elements, we get the following result, where I disk is equal to 1/2 mr squared. So these two are the most important moment of inertia equations that you would need to know, but there are many others. So let's draw a quick table and just label different moments of inertia for uniform rigid objects of different shapes and sizes of mass m. So we have our shape, we have our moment of inertia equation for each shape. Let's now draw these out. If our shape is a hoop, or cylindrical shell, that means you have something like this. It's a shell, and your axis of rotation is through the center. So very important to say that the axis of rotation is at the center. So then your moment of inertia equation is I is equal to mr squared. So that's one option. We have a disk or solid cylinder. The axis can be at the center, so we'll draw the exact same thing. But now it's a solid disk. And we have rotation about the center. We then have I equals to 1/2 mr squared. Apart from that, we want to look at the disk or solid cylinder again. But what happens if the axis is at the edge? That means we have a solid disk but the axis of rotation is now here. So just changing the axis of rotation will change your equation for the moment of inertia as well. So I is equal to 3/2 mr squared in this case. And that's just an example of how changing one small thing can affect the moment of inertia. Another common one would be a long, thin rod. And we'll assume that the axis is at the center. So in this case, we have a long, thin rod of length L, and we have, so let's draw this a little bit better. That's L. We have rotation about the center. And this is going to give us a moment of inertia of 1 over 12 ml squared. If we change the axis to the edge, or the end of the rod, that means we have something like this. Our rod yet again, of length L. But now the axis of rotation is right here, at one of the ends. Our equation for moment of inertia is then I equals to 1 over 3 ml squared. So these are the 5 main moment of inertia equations I believe are the most commonly used. There's a total of 10 common ones that I've placed in the transcript and the downloadable PDF that you can get with pictures of the shapes as well as the axis of rotation. These would be good formulas to put onto your formula sheet, but when you're working with problems, these 5 over here are the main ones that you would encounter. Now, let's revisit the law of conservation of energy of rolling motion. With objects that roll, we already came to the conclusion that we need to consider translational kinetic energy and rotational kinetic energy. Therefore, we define the kinetic energy of rolling motion as Ke is equal to Ket plus Ker. So that means Ke is equal to 1/2 mv squared plus 1/2 I omega squared. If we do not have angular velocity handy to plug into this equation, we can also redefine omega using V equals R omega to get Ke is equal to 1/2 mv squared plus 1/2 I v over r squared. We have Ke is equal to 1/2 mv squared plus 1/2 IV squared over r squared. In other words, we can rewrite the total kinetic energy. We can factor out the 1/2 v squared and get m plus I over r. This is just an alternate way of representing the total kinetic energy for rolling motion. Apart from that, we should also update our equation for mechanical energy to encompass everything we have covered so far in this course. So mechanical energy is now equal to ME is equal to KE plus PE, but now we have ME is equal to KET plus KER. If there's gravitational potential energy, we have PEG, and if there's spring potential energy, we have PES. So now let's go through a few practice problems related to moment of inertia and rotational kinetic energy. In this question, a 1.20 kilogram disc with a radius of 10 centimeters rolls without slipping. If the linear speed of the disc is 1.41 meters per second, find A, the translational kinetic energy of the disc, B, the rotational kinetic energy of the disc, and C, the total kinetic energy of the disc. So we know that this is an energy problem, and we know that there's a disc that rolls and moves. We already have the equations for rotational and translational kinetic energy, so why don't we use those? Let's first draw a diagram of the system, just to get familiar with drawing these types of scenarios, and state our known values. So step number 1. So we can draw the ground here and a solid disk with an axis of rotation here. The disk is 1.2 kilograms, so we have a mass here, but also because it's a rotating object, it has a moment of inertia I. So the linear speed of the disk is 1.41 meters per second. We also have the radius of the disk. And we also know that in order for it to move forward, it has to have some sort of angular velocity. Okay, so let's write down all the values that were given. We already wrote down v is equal to 1.41 meters per second. We don't know what omega is. We don't know what I is. We do know the mass is 1.2 kilograms, and we know that the radius is 10 centimeters, or 0.10 meters. Some important equations for a disk: I is equal to 1/2 mr squared. We know that the translational kinetic energy is 1/2 mv squared, and we know that the rotational kinetic energy is 1/2 I omega squared. So in step 2, we want to apply our energy equations and solve. So to find the answer to part A, we simply use the equation for translational kinetic energy. So KET is equal to 1/2 mv squared. We already have m, we already have v, so we can simply plug in our values. V is 1.41 squared, so therefore KET is equal to 1.193 joules. We've answered the first part of the question. Now we want to move on to part B. So in part B, we're trying to figure out the rotational kinetic energy. So we want KER, which is equal to 1/2 I omega squared. So we do need the moment of inertia, and we do have an equation for that. So I is equal to 1/2 mr squared. We don't have omega though. However, we know V is equal to omega R, or R omega, which means omega is equal to V over R. So we can replace our expression for omega with V over R. So we have KER is equal to 1/2 mr squared to replace the I, and V over R squared. So KER is equal to 1/4. The R squareds cancel, and we end up with 1/4 mv squared. So we plug in our values and we have KER is equal to 0.596 joules. Now that we have both our translational and rotational kinetic energies, part C asks us to find the total kinetic energy of the disk. So that just means KE is equal to KET plus KER. KE is equal to 1.193 plus 0.596. And the total kinetic energy is 1.789 joules. In this problem, a block of mass m is attached to a string that's wrapped around a wheel of radius r and mass capital M. The wheel rotates freely about its axis, and the string wraps around its circumference without slipping. Initially, the wheel rotates with an angular speed omega, causing the block to rise with a linear speed of v. To what height does the block rise before coming to rest? So this is a pulley question, but now the pulley is no longer massless, and we have to consider it as an object. The question gives us several key pieces of information. First, the pulley is a solid disk, so its moment of inertia is 1/2 mr squared. Second, the string wraps around the disk without slipping, so we can relate linear to angular velocity as v equals r omega. Finally, the question states that the wheel rotates freely, so it means that mechanical energy of the system is conserved. This means we can assume that when the block comes to rest, all of its kinetic energy should be converted to gravitational potential energy. So what we want to do is first break this up into initial and final stages and draw a diagram. So initially, we have a pulley, and the axis of rotation is right at the center. This pulley has a radius of capital R, and it has a mass of m. It also has an angular speed of omega that we know. And let's say that the counterclockwise direction is positive. Next, we know that there's a string that's tightly wrapped around the pulley. And there's a hanging block of mass m. We can assume that this block m starts at a height of y equals 0. So just to be clear, these are all initial values, so we probably should have I in front of these values so that we know that these are initial amounts. So yi and omega I are the two that might change. You also have the speed of the mass, which we'll draw in red, vi going up, and we'll say that the up direction is positive. Okay, so it seems like there's nothing else we need to add to this. Let's draw what happens in the final stage. So in the final stage, we have our pulley again. The axis of rotation, the mass and the radius don't change, but the angular speed might. The linear speed of the hanging mass might change as well, so we have a final speed for the hanging mass. And most importantly, this is y equals 0. It means that yf is equal to some sort of height, h. So we're not given any values, we're just given variables. So in step number 2, what we want to do is apply our energy equations. The main goal of this problem is to figure out what height the block rises to before coming to rest. So there are a few assumptions we can make, and that means Vf is probably going to be 0, and omega f is also probably going to be 0. The initial height is 0, and the final height is going to be h. So we can approach this like any other conservation of energy problem. We're going to look at the initial and final energies, knowing that they're going to be conserved. Because we want to figure out the height that the block reaches, we're going to have to look at gravitational potential energy. So we know the law of conservation of energy applies. MEI is equal to MEF. We have the initial translational kinetic energy plus the initial rotational kinetic energy plus the initial potential energy. And we have the final versions for each of these as well. This means we're going to have to write all of these out. Translational kinetic energy is 1/2 mvi squared. KER is 1/2 I omega I squared plus mg hi or yi equals 1/2 m vf squared plus 1/2 I omega f squared plus mg yf. We already know that the final speeds in both the linear and rotational worlds are going to be 0. So Vf is equal to 0 and omega f is equal to 0. So that makes our right side a lot easier to work with. We now have 1/2 mvi squared plus 1/2 I omega I squared plus, oops, forgot to also mention that the initial height is 0. So this goes to 0 as well, and we have mg yf. At this point, we should try to rewrite certain values with values that we know. So we know that we want to solve for yf, which is equal to h. So we're going to substitute that in. We have omega I given to us as omega. We have the initial velocity as v. We do know that the mass of the pulley is capital M, but that's nowhere here. We have the hanging mass as little m, so this is fine. but we do need to figure out what I is. So I is equal to 1/2 of the mass of the pulley, which is capital M, times R squared, so capital R squared. So now that we have all this, we might want to replace all of these values with what we've redefined here. So we have 1/2 mv squared plus 1/2 mr squared. Omega I is just omega squared, is equal to mgh. And we want to solve for h, so that means we have h is equal to, let's see, 1 over mg times all of this on the left side That means I can rewrite this as h is equal to 1 over mg We can either leave it as this, or if you want, you can also say that omega is equal to v over r, and we end up with 1/2 mv squared plus 1 over 4 mr squared v over r squared, and h is equal to v squared over 2g times 1 plus m over 2m. The reason for that is because these r's cancel out. We can factor out a v squared from here and here. And we also have g at the bottom from the first part. So now this is your answer, and that answers the question. In this problem, the moment of inertia of a 0.98 kilogram wheel rotating about its center is 0.13 kilogram meters squared. What is the radius of the wheel, assuming the weight of the spokes can be ignored? So essentially this question is asking us what the radius of the wheel is if we assume it's just a cylindrical shell. So this is a moment of inertia problem. We're given the mass of the wheel, which is, like we said, a cylindrical shell or a ring. We're also given the value of I, so all we have to do is choose the correct equation for moment of inertia based on the shape and solve for the radius. So, step number 1, there's only one step. We're just going to state our known values and solve. So we know that we're looking at a cylindrical shell or a hoop. So we know that I is equal to mr squared. We know that m is equal to 0.98 kilograms, and we know that the moment of inertia, I, is equal to 0.13 kilogram meter squared. So we're trying to solve for r, which is the square root of I over m. R is equal to the square root of 0.13 divided by 0.98. And so R is equal to 0.36 meters. And that's all this question is asking for. In this problem, we have two masses. We have M1 and M2. One's 5 kilograms and one's 3 kilograms. They hang on each side of a pulley of mass capital M. This is called an Atwood's machine. The two masses are released from rest, with M1 at a height of 0.75 above the floor. When M1 hits the ground, its speed is 1.8 meters per second. Assuming that the pulley is a uniform disc with a radius of 12 centimeters, determine the pulley's mass. So we have quite a few things going on in this problem. We have up-down motion, with the two masses and rotational motion with the pulley. We should start with an initial versus final diagram, labeling as much as we can. Then we should probably figure out which energies to look at. The reason why we want to use conservation of energy to solve this is because we have initial and final speeds, because the masses are released from rest and end up at a certain speed. And then they also have different heights. So it has everything to do with gravitational potential energy and also kinetic energy. But now we're looking at three masses instead of just the two masses that are hanging. So step number 1. Let's draw our diagram and state our known values. So I'll probably make this a little bit easier because I don't want to draw the same thing in detail twice. So I'm going to draw the first one in as much detail as I can. So we do have a pulley in the initial stage. This is the axis of rotation. The radius of the pulley, I can say, is R, or capital R as they've said. And this pulley has a certain mass and a certain moment of inertia. Then there's going to be a string that allows two masses to hang. So let's see. The two masses are released from rest. M1 is at a height of 0.75 above the floor. So let's choose M1 to be here. And let's choose M2 to be here. So the assumption is that M2 is already on the ground. And that means this is y equals 0. And the height of mass 1 is at y equals h. So there's quite a few things to label here. We do have the force of tension pulling on each of the masses. We also have the force of gravity acting on each mass. So we have M1g acting here, and we have M2g acting on the second mass. We also know that there's some sort of angular acceleration going this way, because mass 1 is heavier, so it's going to accelerate downwards towards the right side. Let's say that this is the positive direction, just so it's easier, and let's say up is positive. The initial speed of mass 2 is VI, same as mass 1. And there's also going to be some sort of linear acceleration going this way for mass 2 and going this way for mass 1. Okay, so now we have quite a few things. We're going to write down what we're given. We know M1 is equal to 5 kilograms. We know M2 is equal to 3 kilograms. G is equal to 9.8 meters per second squared. We're trying to find the pulley's mass, so we need to find what capital M is. We do know that the radius of the pulley is 12 centimeters, or 0.12 meters. We know that the moment of inertia is that of a solid disk, which is 1/2 times the mass of the pulley times r squared, which means m is equal to 2I over r squared. Next we have the initial height of the first mass being h, which is 0.75 meters, and the initial height of the second mass being 0 meters. We have the final height of the first mass being 0 because it hits the ground, and we have the final height of the second mass being 0.75 meters. Now let's look at speed. We have the initial speed of the first mass is equal to the initial speed of the second mass, and they both start from rest, so it's just 0 meters per second. This also leads us to the conclusion that if they start at the same speed, and because they're all together as one, they're also going to have the same final speed. So v1f is equal to v2f, which is equal to vf, which is 1.8 meters per second, as indicated. Okay, so I think we've covered everything. Now for step 2, to put everything together, we're going to use the energy equations to solve. So we know that this is a conservation of energy equation. There are initial and final speeds as well as heights. We also know that energy is conserved in this system. So that means we start off with MEI is equal to MEF. And there are a lot of things to consider here. We have to add up all of the kinetic energies that are acting on the system. So we have KE, the kinetic energy of the first mass initially, the kinetic energy of the second mass initially, and the kinetic energy of the pulley initially. Plus, you have gravitational potential energy coming from the first mass and gravitational potential energy coming from the second mass. We do the same for the other side, KE1F plus KE2F plus KEPF plus PE1F plus PE2F. So it's getting pretty long. Now comes the tricky part, looking at the kinetic energies of each mass separately. So when I look at the kinetic energy of the first mass, I know that it's not rotating, it's just moving up or down, which means it's only translational, which means it's going to be 1/2 m1 v1I squared. So it's only translational. Same with the second mass. We have 1/2 m2, not m1, m2 v2I squared. So we've done these two. Now we're looking at KEPI. So the kinetic energy of the pulley isn't moving translationally, but it is rotating, so it only has rotational kinetic energy, which means it is 1/2 I omega I squared. Then we look over here at the gravitational potential energy of the first mass initially. It is at a height of h, so we have m1 gh plus the gravitational potential energy of the second mass it's at 0, so we have m2g of y2i. Should probably change this to y1i, just to be clear. Okay, now we do the exact same thing with the right side. We have 1/2 m1 v1f squared plus 1/2 m2 v2f squared plus 1/2 I omega f squared plus m1g y1f plus m2g y2f. This is getting very long. So first we want to take a look at what values are 0 so that we can get rid of them quickly. We know that anything associated with vi, so the initial speeds for both the first and second mass are 0, so we can say these are 0. We also know that the final height of the first mass is 0, so we can go towards the right. The final height of the first mass, oops, not the second mass, of the first mass is 0, so that is 0. The initial height of the second mass is 0, so that goes to 0 as well. So let's write down the simplified version of this, just so it's not so cluttered. We have m1g y1i is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared plus 1/2 I omega f squared plus m2g y2f. Okay, so there's still a lot to go through, but our goal is to figure out what the mass of the pulley is, and that is capital M. So right now, capital M is nowhere to be found, which means we do need to introduce capital M using moment of inertia. And the next thing we want to do is to check to see which terms we already have. So going back above, we do have M1. We do have M2. We do have G. We do have the initial height. We have the final speed. And we have the final height of the second mass. But what we don't have is omega f. So this means we need to replace I and omega f with something else. So I is simple. We know that I is equal to 1/2 mr squared We also know that omega f is equal to Vf over R, since our conversion equation was Vf is equal to R times omega f. And that's basically it. Now we just substitute in and try and solve for M. So m1g y1i is equal to 1/2 m1, let's simplify v1f by just calling it vf. Same with v2f, it's also vf, plus 1/2. I is 1/2 mr squared, omega f is v f over r squared, plus m2g y2f. Okay, so we now have m1g y1i is equal to 1 over 2 m1 vf squared plus 1/2 m2 vf squared plus 1 over 4 mr squared times VF squared over R squared. So the R squareds do cancel out. So it's M VF squared plus M2G Y2F. Okay, so let's move 1 over 4 M VF squared over, just so we can start to solve for M. Everything else can be moved over. Let's keep these potential energies together. Then we have minus 1/2 M1 VF squared minus 1/2 M2 VF squared. So M is going to be equal to 4 over VF squared of, we can factor out G from the first two terms to get M1 Y1I minus M2 Y2F. And we can also subtract 1/2 VF squared from M1 plus M2. Okay, so this is a little bit more simplified. M is equal to, let's put everything together, we have 4G M1 Y1I minus M2 Y2F over VF squared minus 4 divided by 2 is just 2. The VF squares cancel, so this is 2 M1 plus M2. We can now plug in the values that we know. We know G is equal to 9.8. We do know that M1 was 5 times 0.75 minus 3 times 0.75 divided by the final speed of 1.8 squared minus 2 times 5 plus 3. And when you plug that into the calculator, you get 2.148, let's write this better, 2.148 kilograms. And that is the mass of your pulley. So another problem, a solid sphere with a diameter of 0.17 meters is released from rest. It then rolls, without slipping, down a ramp that is 0.61 meters tall. The ball leaves the bottom of the ramp, which is located at the edge of a table 1.22 meters above the ground. The ball leaves the bottom of the ramp horizontally. A. Through what horizontal distance does the ball move before landing? B. How many revolutions does the ball make during its fall? And C. If the ramp were to be made frictionless, would the horizontal distance traveled increase, decrease, or stay the same? So there are 3 questions here that we have to answer. Let's first make a plan. This is a multi-step problem. A sphere rolls without slipping down an incline, and it gains speed. It's then launched horizontally off the edge of the ramp, and from this point onwards, we're looking at a projectile motion problem. At the beginning, we have a ramp and it's rolling down, so we might have to look at angular terms and rotational rolling motion. But after it's released from the ramp, we can use conservation of energy to determine the horizontal launch speed of the ball at the bottom of the ramp. And then we can use linear kinematics to solve for the horizontal distance traveled, especially because the ball leaves the bottom of the ramp horizontally. So step number 1, we really do need a diagram for this, and we really want to state all of our known values. There also seems to be more than just an initial and final stage. There's an initial stage where you're letting go of the ball from rest and it rolls down the ramp, and there's this intermediate stage where the ball is launched from the end of the ramp off the table. So we'll call this the launch phase, and then at the end you do have your final phase where it just reaches the ground. So there's 3 snapshots in time that we want to look at: initial, launch, and final. So step number 1, we want to draw a diagram and state our known values. So first, we have a table. So we'll call this the table. And it's resting on the ground somewhere. Like this. We'll extend the ground so that we have a proper projectile motion. So we have the table, the ground, there's a ramp on top of the table. So let's draw this in black. So the ramp starts at a certain height, it extends to the edge of the table, and it's probably something like this. See if I can draw this a little bit more curved. So this is our ramp. We're told that the height of the table is 1.22 meters. We're told that the height of the ramp is 0.61 meters. So now all we have left is to look at the initial stage, which we'll call I. And we have a ball here with its center of mass. The initial speed of the ball is 0 meters per second, and the ball is going this way. So it goes down, down, down to the edge of the ramp. We'll have the center of mass here, and it's launched horizontally. And we'll call this stage stage L for the launch stage. We know that the speed here, we can call this VL, is equal to an unknown amount. That's part A. We'll need to figure out the launch speed in order to figure out the horizontal distance the ball moves before landing. So after this, we have a projectile motion problem. And we have the ball landing here. And we'll call this the final stage. We should also label this as the distance traveled by the ball from the edge of the table to where it lands. So have we completed our diagram? Seems like we've labeled most of everything, but we're missing something very important. It's the coordinate system. So let's add in a coordinate system where this is x and y, and this is positive. We should probably have acceleration going down. So let's say acceleration is down. We might also want to choose where the height is equal to 0 for our potential energy problem. When I look at this problem, I know that from I to L, I'm looking at a change in potential energy because the ball has essentially dropped a distance or a height of 0.61 meters. So why don't we say the bottom of the ramp is at a height of 0? That would help a lot because we'll be able to judge gravitational potential energy for the first part of this question from I to L. So that covers pretty much everything in the diagram. We do have to state our known values now, so let's clarify all of them over here. We have our initial stage, and that means we have an initial launch speed or initial release speed of 0 meters per second. We don't really have the mass of the ball, so we'll put a question mark here. The initial height is 0.61 meters for our ball. In the launch stage, we have VL being an unknown amount, but we do have HL being 0 meters. Then we have our final stage. We have acceleration is equal to negative g, which is equal to minus 9.8 meters per second squared. We don't know what delta x is, and that's what we're trying to find. And we know that delta y is equal to negative 1.22 meters because we've set our 0 at the table's height. Other equations that we might want to use, we know that I, and this is special, we do have to look at a table for our moment of inertia. The moment of inertia of a sphere with its axis of rotation at the center is 2 over 5 mr squared. We are given the diameter of the sphere instead of the radius, so we do know the radius is equal to d over 2, and we're given that the diameter is equal to 0.17 meters. Okay, so that does cover everything. We can move on to step number 2. In step number 2, we really want to determine the horizontal launch speed. So the only reason why we want to use the conservation of energy here is because we're told that the launch speed is completely horizontal, which means that whatever happens, your final speed that you calculate is going to be fully horizontal, and we don't have to worry about any vertical components. So looking at the initial and launch phases, we see that there's translational and rotational kinetic energy involved, plus gravitational potential energy. So we're going to set up our conservation equation. MEI is equal to MEF. We have the initial translational energy plus the initial rotational energy plus the initial gravitational potential energy. Then we have KE T at launch plus KE R at launch plus PE at launch. So translational kinetic energy is 1/2 m VI squared. Rotational kinetic energy is 1/2 I omega I squared. So just looking at this, we do need to label omega on our diagram, so we forgot the angular speed. So let's put a little turn here and have omega I. And we have omega F here as well. Okay, so then we have mg hi. Then we have 1/2 mvf squared plus 1/2 I omega f squared plus mg hf. And probably shouldn't have labeled it as f because we used launch here, so we have mvl squared I omega L squared plus mg h L squared. HL, not squared. So now we want to go through and see if there are any zero values. We know that the initial speed of the ball is 0 because we released it. We also know that the angular speed is going to be 0 because it hasn't even started rotating yet. So we know that omega I is also equal to 0 radians per second. Let's put that up there in our list of knowns. The initial height is not 0, but we know that the launch height is going to be 0. So that is 0 because HL is equal to 0. The rest are not 0, but we also need to solve for VL. So we have a simplified version, mghi is equal to 1/2 mvl squared. We need to replace I with our definition of I, so it's 1/2 2/5 mr squared. We don't have omega L at all, so we need another way of representing omega L. So we do know that VL is equal to R times omega L. So omega L is equal to VL over R. So let's replace it with that. And that's it. We can now solve for VL. So we have mghi is equal to, we can factor out a VL squared first from both, which means we have (1/2) m plus 1/5 m. This means I have mghi is equal to mvl squared. This is essentially just 5/10 plus 2/10. The m's can cancel out on each side. We end up with ghi is equal to VL squared, 7/10. So VL is equal to the square root of 10 ghi over 7. We can plug in the values that we know. So 10 times 9.8 times the initial height, which is 0.61, divided by 7. We have our initial launch speed being 2.922 meters per second. But that isn't our answer. We're trying to figure out the horizontal distance the ball moves before landing. So, step number 3. We want to determine distance traveled using linear kinematics. So to answer part A, we need linear kinematics, so we need to split our analysis into the x and y directions. So remember, we have our ball like this, and it has a launch speed. which also means it's going to go down onto the ground. And it travels a distance of delta x. We're also told that the height here, delta y, is equal to 1.22 meters. But because we saw this as y equals 0, it's equal to negative 1.22 meters. Apart from that, acceleration was downwards, and we had our coordinate system like this. So that means we need to look at each of these directions separately. We have our x direction, and we have our y direction. So in the x direction, only one equation works. It's VL equals 2 delta x over t, or delta t. So that means if we do want to find delta x, we need to multiply VL by delta t. So that means we need to find delta t, and the only way we can do that is through the y direction. So we're given delta y is equal to negative 1.22, acceleration is equal to negative 9.8, the vertical velocity is equal to 0. So let's verify this. VLYI is equal to 0, and we're looking for t. So we have 3 values, which means we can use kinematics equations to solve for the fourth. We have to figure out which kinematics equation to use that has delta y or delta x, a, v, I, and delta t. So the one I would use would be delta y is equal to v L y I t plus 1/2 at squared. This is just 0, so that means we have delta y is equal to 1/2 at squared. T is equal to the square root of 2 delta y over a, which is equal to 2 times negative 1.22 divided by negative 9.8. So t is equal to 0.499 seconds. Therefore, delta x is equal to VL delta t. Delta x is equal to VL, which we've calculated before to be 2.922 meters per second times 0.499 seconds. Delta x is equal to 1.458 meters. And that is the horizontal distance traveled by the ball. So next, part B is asking us, how many revolutions does the ball make during its fall? So let's say this is the answer to A. Step number 4, we need to determine the number of revolutions that the sphere spins. So in order to find the number of revolutions for part B, we need the angular speed. So we can use VL is equal to R omega for this, which means omega L is equal to VL over R, we have 2.922 divided by the radius, which was given as d over 2, or 0.17 over 2, and omega L is equal to 34.376 radians per second. So now we want to be able to find the angular displacement. Delta theta, which is simply equal to omega t, because we know that omega is the change in position over a change in time. So delta theta is equal to 34.376 radians per second times 0.499 seconds. Delta theta is equal to 17.153 radians. But we want the number of revolutions, so there are 2 pi radians in 1 revolution, so delta theta is equal to 2.730 revolutions. So therefore this answer is part B. There are 2.73 revolutions that occur before the ball hits the ground. Now step number 5, we do have a last step because there's part C. It's asking us if the ramp were to be made frictionless, whether the horizontal distance traveled would increase, decrease, or stay the same. So step number 5. We want to think about a frictionless surface. So with a frictionless ramp, the sphere would slide instead of roll. So sphere would slide instead of roll. It would therefore store no energy in its rotation, so all of its gravitational potential energy would become translational kinetic energy. So there would be no KER at all, and all of its gravitational potential energy would essentially become the translational kinetic energy for the ball to launch from the table's edge with a higher speed, since the rotational kinetic energy is 0. So therefore, the landing distance would increase because of this. So just to repeat, if you have a frictionless surface, the sphere is going to slide instead of roll. Because it slides and doesn't roll, it means there's no rotational kinetic energy, so that means there's going to be all of the gravitational potential energy turning into complete translational kinetic energy for the horizontal launch. So therefore, larger value of a launch speed is directly proportional to a larger distance traveled. So therefore, a frictionless surface would increase the horizontal distance traveled by the ball. And that answers part C.